All right, so we're going to study severe anti-gravity translator and secure engineering for data.
Okay, so welcome to lecture 2. So last time I didn't quite finish the whole story, so I'll spend the first, hopefully only 10 minutes, but let's see how things go. Minutes just wrapping up what we talked about last time, and then we'll go into something new, which is the double copy. But yeah, the theme is still the same, that we want to fix scattering amplitudes. We want to see what kinds of things we can use to fix scattering amplitudes. So it didn't work. No, I can.
It's working.
Yeah, it's working. Okay, good. So last time we looked at Born-Infeld theory in particular, and we saw this example of this helicity conservation symmetry, which we called EM duality. We understood how generalized unitarity can help us talk about amplitudes at loop level. We fixed the tree level amplitudes using some recursive argument. And yeah, so we left off at the point where we were just going to put the tree level amplitudes together to make a loop level amplitude. Okay, so before that, this was the 3D recursion where we reduced the 4-dimensional momenta to 3 dimensions, and we said that it has to vanish if it's a duality violating amplitude, and that fixed all duality violating tree amplitudes to 0.
But what about the duality not violating?
We did not say anything about those. Yeah. And I won't say much about those, but I'm happy to show you exactly how those are fixed. It's a different style of recursive. They are fixed, and they are also fixed using a recursive argument. It's just a slightly different recursive argument. Yeah. Okay.
Also like this PCFW style.
It's a bit different because you can't actually recursively construct those amplitudes. You have to construct their super partners, and then they get fixed by the supersymmetry Watt identity. Yeah.
Supersymmetry is important.
Right. But because Exactly. So because the vector part is a consistent truncation, you can always, just look at the vector part, and that's Born-Infeld. Yeah. Okay, good. So I was talking to Gautam, and he suggested that I give you another example of a symmetry of such a symmetry amongst vectors, this kind of helicity preservation. Just to show you that it's not that special that this exists. I mean, there are other places where this naturally shows up, and you can see it in terms of the amplitudes. And one of these examples is a supersymmetric nonlinear sigma model. So if you have some symmetry breaking, you get a Goldstone mode, and the Goldstone mode says that your amplitude will vanish in the soft limit. Okay, because that's Weinberg's soft pion theorem. So you can use the fact that the amplitude vanishes to fix all of the amplitudes in this supermultiplet, and you'll see then that you have to have the vectors carrying a charge like this, and for charge to be conserved, then you have to have equal numbers of both of these. Okay. So there's still some kind of So all this to just say that there are other examples where you get these kinds of charged vector type symmetries.
So once you get the style, you get a supersymmetrize the theory, and then use the fact that tree amplitudes will change.
Yeah, so in this particular example, it's a bit more involved because once you supersymmetrize, you also have 3-point interactions which tend to spoil your soft behavior. So you have to be a bit more careful when you make these recursive arguments. That is not the case for Born-Infeld. So this particular model is a bit more complicated, but it's, yeah. So if you study what R symmetries are present and not present, which ones are global, which ones are built in, etc., you find that indeed these have to have a charge.
Okay, so just in this full theory, or in some truncation of the theory?
In the full theory, yeah.
What is the method compared to what cannot consist truncated?
That these, it can't be consistently truncated for the reason that you have 3-point amplitudes that have a gamma plus phi interaction. So stuff like that doesn't exist when you supersimplify Born-Feld. Yeah, you only ever have 2 photons and 2 some other particles. Yeah, so then you can always at tree level forget about the other particles. Yeah. Right. So this is why this model is slightly more complicated, but it still has this structure that you have to preserve helicity.
Now we are looking at different models.
No, this is just an example to say that there are other theories where you have this type of charged vector symmetry. And that many of the methods we talked about in the last lecture, you can use for other stuff as well. It's not that.
Let's look at, even though this theory has many parts, let's just look at the amplitudes that involve only
The gammas.
Then those will by charge propagation.
Right. Okay, so this is where we were at. In the last lecture, we had constructed these tree-level amplitudes, and we had fixed the tree-level amplitudes using the fact that they needed to reduce in the massless limit to some supersymmetric theory. And we were at the point where we knew how to construct the integrand. Actually, we haven't done this yet. But yeah, so we have to do these 2 steps. Okay. Now, the pieces that we were going to construct the integrand with were these vertices over here. So I'll remind you that we were interested in constructing the all plus photon amplitude and the all but 1 plus photon amplitude. Okay. And to do that, we needed to look at cuts like this, right? So this is just this is a representation of the integrand, where now I've broken it up into lots of internal scalar loop amplitudes, right? So this is the only possible diagram you can have when you have all external positive helicity photons. Yeah. Now it's very easy to just use these rules, write down what the integrand is, do the integration, and you get this answer over here. And while it might look a bit complicated, one thing to see, which is very easy to see, is that there's nothing in the denominator that depends on momentum. Okay. So this is a fully local answer. It didn't have to be. It needed to only be a rational answer, but it's a contact term, which means that I can indeed remove it by adding a finite local counter term to my action. Yeah. I didn't say it was easy. I said that it's possible. It's okay. Actually, it's not that hard. It basically requires one to note that this is. I mean, what you want to do is change this factor of mu squared to the n, absorb it into the d to the 4 minus 2 epsilon L, and so make a larger dimensional loop integral, and then you can do it. Then it's just a scalar loop integral. Yeah.
I was thinking you would sort of sum all of these diagrams, get a self-entering kind of direction, and then do that.
So you don't need to sum any diagrams because this is the only one at this.
But with some number of photons.
Yeah, at each n, there's exactly one of these that you can draw.
I was just wondering. Anyway, that's it. Yeah. I was wondering if there was something easier about the whole sum of all these processes. It promised to.
Yeah, I'm not sure that there is.
So, should be sorry.
Yeah.
I'm just going to take you a step back to your last one, because
yeah.
I know last time when we stopped, you were saying, look, you were doing loop diagram. You said, look, there's a cut contribution,
yeah.
and then something more.
Yeah.
And then you spent quite some time so that setting things up so that we could decide whether there could possibly be a non-local contribution, and that's something more.
Right.
And then I lost the thread between that and what you're saying now.
Okay.
The statement is nothing non-local for this case.
Exactly. So now when we do the full computation, one finds that actually there was no non-local piece. Mm-hmm. But there was no way to see this from the beginning. You had to actually do this. Yeah.
And this is now what then? This is the full answer.
Yeah.
Is there no ambiguity in terms of the non-cut contribution, some rational term you could have?
So this is the rational.
This is the extra rational term.
Right. Up to order epsilon. Yeah.
So what happens?
So this is the integrand and this is the integral after doing the integral.
This is an analytic.
Yeah.
No, so then
Yeah.
we did not have logarithmic.
So the log paths would exactly be the cut constructible path. So to have a log, you would need to have a physical two-particle threshold, which, because these are duality violating and the tree level is duality preserving, you don't have. So you only have a rational contribution. And then the question is that rational contribution local or not local? Yeah. So you don't have a log for precisely that reason, because there is no physical two-particle threshold you can ever reach.
But what was this thinking about?
So this
So
so the scalar particles are on shell, but that they themselves are in so they come with these mu squares, right? So the mu square is 0 in 4 dimensions, in strictly 4 dimensions. So you have this proportional to a power of mu square. So precisely you find that you don't get any parts which are divergent in 4 dimensions, which normally would come with a log, which tells you there's a physical way of getting to that that cut. This is saying that there is no physical way of getting to the cut in 4 dimensions. Yeah. So
Scalars, slightly better scalars.
So the scalars, basically you're replacing the inside vector loop with a scalar loop using some supersymmetry. The fact that these vanish in n equals 2 and n equals 1. Yeah. Okay. So so this is for the all plus. For the all but one plus, you have 2 types of contributions, one with this white vertex and one with the gray vertex. The details are not important. I mean, it's basically, there are only 2 types of diagrams at any endpoint. You can put them together in the same way. It just looks a bit worse. You get an integrand, you integrate it, and you get these 2 contributions. And this is the final answer where you get some 2 contributions that you sum together. Yeah.
So tree level, I understand why the supersymmetric theory and non-supersymmetric theory say
Yeah.
But at root level, you get different answers.
That's right.
So you're doing the loop calculation in the supersymmetric theory or the original?
In the original theory, so you have something like, you have some amplitude with, let's say, just 4. So you have okay, this is very schematic. I don't know, there are no 3-point interactions, but you have a vector loop. You have a fermionic loop.
This is the supersymmetric.
Yeah, in a supersymmetric theory. And then you have a scalar loop. Right? And so for n equals 2, you'll be a sum of vector plus 2 fermion plus scalar. N equals 1.
Oh, this is what you told us.
Yeah.
Sorry.
Yeah.
Thank you.
Yeah.
Yeah.
So you rearrange it.
Thank you.
Yeah.
Sorry.
No worries. So that's why you've replaced this by a scalar loop, and that's why you can do these calculations. And when you do them, again, unlike the last time, you now have, you can see over here in the denominator, there's some Mandelstam, right? So here now we have to check what exactly happens on this pole, and is it a truly local contribution, right? And one finds that actually this factorizes correctly into this counter term times just the regular Born-Enfeld vertex, right? So which is this? This is to say that if I add a local counter term here, a local counter term here at all n, then I can remove these contributions completely. Okay, in these 2 helicity cycles.
That was the same counter term you needed for the first.
Exactly. So crucially, it was the same exact counter term I needed to remove the all plus. Yeah.
What was on the last slide and what was on the slide before?
So the last slide was this amplitude. The slide before was this amplitude. And I'm just saying that here there was a pole, but that pole is explained by the fact that this has a non-zero local counter term. Yeah. So it's just the regular loop with a tree attached to it. Yeah.
Sorry, the one thing I didn't quite appreciate is in the previous case, all plus case, that polynomial piece was actually divergent. It's epsilon.
No, everything is rational. Everything is non-divergent because they're all duality violating amplitudes.
But I'm calling it counterterm just because it's local. I mean, it's
Yes, yes.
that seems to work. Okay.
Yeah. Means you can actually add something to your Lagrangian that removes it. That's kind of how I'm using the word counterterm. Yeah.
The fact that the symmetry is kind of a linear symmetry rather than it is not there in full theory, it doesn't show up in some non-local terms that scattering.
Right, which it could have, right? I mean, all of the reasons you have to believe that the symmetry exists at tree level stop working once you go to loop level.
Yeah.
Yeah, so there's no reason for this to have happened. It's kind of curious that it did actually.
I think you write on the Lagrangian that gives it
Yeah, it's not too hard to write down some term in the Lagrangian that gives you
roughly what is it?
like,
Log of F's,
yeah, it's like some contraction of all F pluses.
F pluses.
Yeah.
F pluses.
F pluses where you take the mu and you separate it into spinor indices with some sigmas. So that on shell, that F only gives you a gamma plus. It doesn't give you a gamma minus.
Not familiar with it. Is it
Yeah.
central or something? No.
Yeah, kind of.
Okay.
Yeah.
Okay.
Yeah.
Okay.
Yeah.
And it's not a term, it's not something which will package itself into the bond infill. Is it something which is
Not a,
gas type or is it an acceleration parameter? Maybe.
well,
Right?
yeah, it's
By the way, in the air, some move further there.
It would directly have.
I think that's right.
It is finite, the lambdas have to come where they do something like that.
Is that
So there are some, no, sorry, there are some derivatives on those Fs. Yeah, it because I mean, and that makes sense, right? Because at tree level, you were F to the 4. So you can't possibly at loop level, yeah, continue to be, and the coupling is dimension full, exactly, yeah. So you have to have extra derivatives.
You have to have n extra.
Yeah.
Two n extra.
Yeah, which is these, exactly these derivatives. I mean, these are extra from this part, which is just the F part.
Because each coupling has dimension minus.
Yeah. So you have to, I mean, it's like the usual higher derivative EFT kind of approach. Yeah.
Okay, and then you should go on, but then it's all the more, so since you're getting these terms, you might expect, they're not part of bond and fill, you might expect if you start violating your
Exactly.
electromagnetic.
Right.
well,
Exactly.
Right, so these terms will presumably not respect.
So these are the ones that you need to add so that it is like.
So no, but a priori you would expect them. There's no reason to expect them to, but it turns out that they do. Yeah, that's what I'm trying
This
to
is what cancels the violation.
Exactly. So it's possible to cancel that. Yeah. The crucial part is that it is possible to cancel.
Suppose I was the guy who said, I'm not going to add anything unless needed due to infinity.
Yeah,
This
then,
would be part of the answer.
yeah, then this would just be part of the physical
And
answer.
it would happen that although they are not of bond and fill form, they preserve this.
Right. So this is saying it is possible to write down a Born-Feld theory. Or again, this depends on how you're defining Born-Feld beyond the leading order. But if you define it to be something that has, the question is, can I define it to be something that has EM duality to all loop orders? And the answer preliminarily is yes.
Could I summarize?
Yeah.
Born-Feld at tree level preserves.
Yes.
Born-Feld with your definition of Born-Feld. You're working dimensional regularization and nothing else to that. It violates this.
Yes.
But that violation is of the form that can be removed by adding to Born-Feld.
A finite local counter term.
At each order.
So if I do that.
Yeah.
Because I don't
And
have
it's-
to, right?
yeah.
I would buy.
Yeah.
And these by themselves violate.
Yeah.
But they still do cancel.
But by the way, that can be true even of, sorry?
Anomalies are over.
Exactly. So this can happen even with supersymmetry.
Yeah, these are two separate questions.
Yeah.
Because you may say, okay, I choose to define this theory with no counter, no infinite counter, just whatever comes out, and then you violate it.
Right. But I mean, you have to be careful. You have to be careful about this because it's also a question of whether your regularization scheme respects the symmetry or not. So you can do this even for supersymmetry. Use a non-supersymmetric regularization scheme. You won't find that they satisfy the supersymmetry word identities unless you add a local finite counter term. So, I mean, this is exactly the same story.
Okay.
Yeah.
So now those originally established and normalized for the theories.
Yeah.
Originally by using non-engaged direct counter term.
Good. Yeah, exactly.
Regulator, having non-engaged direct.
Yeah. Yeah, so this, I mean, if this happens with a gauge symmetry, that means, and I mean, sorry, if this doesn't happen with a gauge symmetry that you can remove it as a local contour term, that means the theory is sick, right? But I mean, this is not as important as symmetry. So it's, if it's violated, nothing horrible happens. But
the local answer came from the first, right?
yeah, this is just a contact
So
term.
that is anyway preserving symmetry.
No, this is all plus, right? It needs to have equal number of plus and minus. So this would have to, this vanishes at tree level,
What number of
plus and minus helicities.
so that also, so what you say is you have to say what is in and what is out.
They're all outgoing when I say that.
Okay.
Yeah, that's the convention, is all outgoing.
If n is incoming, then pluses should remain
Right.
plus, then everything should be plus, right?
Yeah, yeah.
They're all out.
Yeah.
So if they're all out.
I mean, you're using crossing symmetry. So you could instead think of it as plus, some of the pluses going in and yeah. Yeah, it would just be not as nice to state because the helicity flips when you flip the momentum.
And
Yeah.
then what about the other guy? Then? The other guy was a form that was not lucid, right?
Yeah, so there you had a pole, but on that pole, it looked like this contact term times the regular Born-Enfeld vertex.
What is that? What is
That vertex is gamma plus gamma minus gamma plus gamma.
plus point.
Yeah, exactly.
You're drawing two pluses, then
Yeah, this is the 4-point amplitude for Born-Enfeld. So it just looks like this. This is in spinor helicity notation. So it just looks like this times that local contact term. Yeah. So
nice,
yeah, so you can just add local things
nice.
and remove both of them
Now,
if you want to.
two minuses, symmetry the same.
Good. So when you have two minuses, you might still violate duality symmetry. That depends on what n you are at. As long as you violate duality, you won't have a cut. So your amplitude will be rational. But all of this will fail. So the fact that we use the supersymmetry to say that I can reduce my vector loop to scalar, that first step won't work anymore once I have an MHV amplitude, right? So in that case, we can't use the same methods, but I will say just this one thing, that is, if the following factorization works, that all the poles in one loop look like one loop times tree, then this procedure, I mean, just the fact that these two were local will remove anything else. Okay, but yeah. Okay. So yeah. So
Yeah, can you say that it is?
yeah, I was just saying that beyond this helicity sector, so MHV and beyond, as long as this type of factor, as long as the analytic structure is the following, that if you have a pole, it looks like a one loop times a tree. If that structure is continuous for the other helicity configurations, then you can see that this is for MHV. These are the types of poles you get, and so you can always remove it. Exactly.
Then the vertex.
Yeah.
Preserve the symmetry.
Yeah.
And then the three vertex.
Exactly. Exactly.
If this pattern holds, then
Yeah.
you would say that it is
You can always do it for all of the others. Exactly. Yeah. Yeah. Okay. So this is all I wanted to say about using generalized unitarity to talk about this tree level symmetry. Okay. There are a lot of questions you can ask as follow-up. We are sort of going to focus in on this last one over here, which is another way of talking about Born-Enfeld theory is the double copy. Okay. And I'll explain exactly what that construction looks like. And then I guess one question could be, is EM duality obvious from that construction? But in particular, it also so the double copy construction gives us a way of talking about Born-Enfeld beyond, or any theory really, beyond the leading order. So it allows us to talk about high derivative corrections. So that will be the next place that we are headed. Yes. Okay.
This is a very initial question.
Yeah.
So what is the status? Do you know the status of this symmetry? I mean, higher loops or things like that.
At higher loops, we don't know.
What is the status of the theory?
I mean, it's highly boundary.
Yes.
So,
So this is why, like, understanding what you mean beyond the leading order is a bit, it depends on how you define the theory in the first place. I mean, this is true of any EFT. Depends on what symmetries you're holding sacred and which ones you're saying, do these exist or not? Right? So if you take the quote unquote sacred symmetry as being it generated by the double copy, what do you get? Yeah. So this is
Actually, I have something related to that because we were bringing up, but since at one loop you started seeing these acceleration terms, right? Then from the perspective of some underlying theory whose low energy limit could be DBI, like string theory, you would have to reliably compute at the one loop order, also include those acceleration terms anyway. Right? Because that will decide what the counter term actually is. So in a sense,
but those would give you even higher order. Those would give you even higher order contribution.
I mean, the counter terms you got at one loop would have to be
in the two.
Their actual values would have to be decided in the context of the higher theory, right?
Yeah.
So I'm just saying, already at one loop, the DBI calculation by itself, becomes susceptible to what the UV conviction is, right? Which we know must exist.
Yeah.
So in a sense, the really universal part is just the tree pattern. Sorry, you just don't understand.
Yeah.
What is the one of the explanation?
And that was what was said, right? This so-called counter terms that
will be higher derivative.
Yeah. But those would come from the X also, right?
this dimensional, right? If 3 level gives you just X to the N, and then you put in N vertices, each of which is an alpha. You need it.
Okay.
N extra for the P square. That's all the loop.
Yeah.
But the large N is
That's fast. It's propagated.
Okay. So
the final answer has to depend on N copies.
Yes.
N copies.
dimension.
So there have to be N square extra. 2N square.
Extra derivative.
Extra.
Yeah, exactly.
You are right, sir.
Yeah. Okay. So let me just give you a quick sort of
Just follow up on that.
Yeah.
So you can compute the one loop for photons gathering in string. Does it or does it not preserve your whatever?
I don't think I don't know what that gives you.
This somebody's calculating it. I mean, you could just look it up.
I don't know who has, I guess. I mean, yeah, someone probably has, but I don't. I haven't looked at it.
Four photons gathering, one brain, one deep brain, and string.
Yeah.
Okay,
I think just from the type one, if you are careful,
you could get the answer, or just do it that to be very. Somebody is this calculation. String theory. So Sandeep's question was, you're changing the definition of the theory as you go along. It's interesting to know whether string theory
Preserves it or not.
Yes.
Yeah, that's worth checking actually. I haven't looked at it.
She wanted the one. Yeah, maybe.
One loop.
Yeah.
Yeah.
Yeah, so and just a follow-up. I mean, certainly it is pendency on amplitude will bind it. I mean, if you allow not just the ball and fell is capturing low derivatives.
Yeah. But that's yeah. But I mean, there you have to be careful about what you are asking of your regularization scheme.
No, I'm being strict there.
No, I'm aware, but I'm saying in this calculation, what have you said your regularization scheme respects and what it doesn't respect?
Okay.
That will
variant question. Right?
Yes.
The answer.
Yeah. The answer is in Okay. So right. So let's do a sort of historical introduction to what the double copy is. Okay. So the sort of origin of the double copy was the idea that we want to understand gravity. Gravity is very gnarly. It has bad vertices. It has more diagrams. It has just generally it's harder to deal with than Yang-Mills. I mean, if you just write down the perturbative gravity Lagrangian, then it has, terms at every endpoint, unlike Yang-Mills, which looks very nice and compact. So all of these things make it harder to do traditional methods in gravity, right? What makes it simple or possible to calculate amplitudes in gravitational theories is the double copy. So the double copy is the structure that you could either think of in theory space or just at the level of amplitudes, which says that there is this way of multiplying two theories to get a third theory. Okay, so I'm using theory very loosely over here. Really, what I mean is that there's a way of getting amplitudes in theory C by multiplying amplitudes in theories A and B. Okay.
I mean, I've heard the statement a lot. I've never personally.
I'll give you some reasons to believe that it's true. Hopefully. Yeah, at 3 point, it's really easy to see. It's literally just the square. So if I take 3 point gluonic amplitude, this is actually 0. One of these has to be a minus. Sorry about that. But if you take this amplitude whole square, that gives you this graviton amplitude, 3 point.
What is this?
Yeah.
Say a little bit more about what the color in the statement.
So this is all color ordered on this side. Yeah. And what the double copy does is sort of removes the color. So here you start with a color ordered object, and here you end up with something that is permutation symmetric. Yes. Not in this exact. So 3 point is very easy. So it's literally just a product, no sums, nothing, of two things. Yeah. So if you take the same one and multiply them together, you get the gravity.
But the product is in permutation symmetric.
Yeah.
Okay.
Yeah. But that's because, yeah, color ordering at 3 point is just like flipping these gives you a minus sign or doesn't. So on this side, it doesn't because you squared it. Yeah. Anyway, so 3 point, it's a very trivial sort of statement. Everything is fixed by Lorentz invariance on either side, and it's not very impressive. Yeah, sorry, one of this is minus. This is just Einstein-Hilbert. Yeah.
What about the other point that gravitons could have?
So with matter or?
No, just graviton, 3 point graviton.
So the only other one would be plus minus minus for all graviton 3 point. 4 dimensions.
These are the 3 types, right? There are 3 types of vortices. The index structure for the graviton.
So I'm not sure what you mean by that. For the simple reason that there are only. Okay. But I'm in 4 dimensions. I'm in 4 dimensions. You could write one.
4. Okay.
You could write one down. You'd have to start with a different vertex.
So that's R2.
That's higher derivative.
That's fine. But I think say you take the R2.
Sorry, so that would still not give you a 3 point interaction. It could give you 4 point interactions. Still, I mean, you would because the 3 point structure for 3 spin 2 particles in 4 dimensions is fixed by little group scale.
But wait,
right?
But the parity violating term gives you at least one other structure. Right?
It gives you the parity. Sorry, the parity violating term is exactly the plus plus plus, right? So that would come from like f cubed on this side.
Wait, sorry, in 5 dimensions and higher,
Yeah.
certainly true that there are 3 possible graviton 3 point structures.
Yeah.
That comes from Einstein.
In 4D also this is true if you include the parity violating one, which I'm not going to be looking at.
Okay.
But it is also higher derivatives.
Parity violating, that's fine.
Yeah.
But I think Amit's question was, let's take one of those guys, which you're not going to be looking at.
Yeah.
Can that also be
Yes.
as square of something?
Yes, it comes from the square of f cubed term on this side, not from Yang-Mills. So f cubed. So f cubed in Yang-Mills, just like on this side, you get a parity violating thing where you get plus plus plus. Yeah. I mean, usually people don't look at it because it's non-supersymmetrizable on the Yang-Mills side. But it exists, like you said, and so you can write it down, and the square of that will give you this. Yeah. Yeah. Okay. So
Obviously, this is much more than saying that If I have two vectors and I simplify them, I get string 2, string 0 in the antisymmetric form.
Yeah, so that is at the level of the what are the states. The level of what are the states is exactly what you said.
But
Right?
of course, it's much more.
Yeah, at the level of the amplitudes, it's much more than that.
But at 3-point function level, it may be almost that.
At 3-point function level, it's basically that. Yeah.
I was wondering that because the propagators are sort of okay, one more piece essentially. So everything is in, but I guess the vertices are all the same.
The vertices you have to be much more careful about, but at the level of 3-point amplitudes, it's very simple because everything is fixed by what the external states are. Yeah.
The number of 3-point amplitudes can become counted by doing some group theory.
Yes.
And that's group theory for 3-point, I think we just.
Yeah, exactly. So this is why this is very simple. And for the, yeah, so, okay. I don't have it on the immediate next slide, but once you add more particles, it's different. And it's no longer just the square. I mean, even the mass dimension wouldn't work out if it was just the square. Yeah.
Must want, but there's some string theory way to do this, right? Because
Good.
open strings join.
Yeah.
Strings.
Yeah.
It's just
So we'll, yeah, I'll that's in a couple of slides, so I'll comment on. Okay, but yeah, the basic idea is that you can connect theories in this way. And when again, you can connect amplitudes and theories in this way. In certain cases, it goes beyond tree level. And yeah.
So what is the generosity? Suppose I write on any let's say a 4-point, or an R to the 4 with some number of elements.
Yeah.
Can every such 4 graviton amplitude be written as?
It's unclear, I would say.
Unclear.
It's unclear that that is true. Yeah. It's definitely true that you can't double copy any Yang-Mills vertex. So it's not like anything can be put into the double copy, but it's not that clear whether everything can be written as a double copy. Yeah.
People put down some consideration for that, right?
Yeah.
They agree,
Yeah. 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 So we wrote down some consistency conditions, which also I'll comment about in just a bit. Okay. So maybe this is too advertisational, but I just wanted to put this up here that it's being used a lot, the double copy, to do some reasonably impressive things. And some of it is just even before doing the double copy, just the fact that you know that Yang-Mills to all orders has this structure that it can be double copied. I'll tell you exactly what that means in a second. Just that is constraining enough to construct pretty high point Yang-Mills amplitudes, and really Yang-Mills, not even supersymmetric Yang-Mills. Yeah. And then after the double copy, of course, you can do things in gravity. You have these higher loop computations. You can do some scattering angles, impulses, other
this
things.
is just the fact that the Yang-Mills allows for the double copy.
Yes. Yeah. And not just Yang-Mills, there's some amount of QCD as well. So if you can, I think single, yeah. So like 2 fermion amplitudes, sometimes 4 if it's a special amplitude. Okay. Good. So we'll get there in 3 slides. We'll see that Yang-Mills isn't the only thing that can be double copied. And one of the other things that can is pions. Yeah.
And it's in a 1-to-1
No, I don't know. I think I can only think of 3 reasons. I think my brain stops working. Yeah. Okay. So when listening to talks about these subjects, there'll be these sort of 3-letter acronyms that show up, either KLT, BCJ, or CHY. Yeah, this is another example of how my brain stops after point 3. But so yeah. So anyway, these are just various formulations, and they all agree at 3 level. And beyond that, beyond that, it's unclear whether or not they do. So this goes back to Sandeep's question, which is that this in string theory, that where you take open string amplitudes, put them together with some kernel, and that gives you closed string amplitudes. And this is a property of the open string integrals and the fact that they satisfy some monodromy conditions. Okay. So this KLT formula is mostly what we'll be talking about today. The more powerful one is BCJ. This is by Born, Carrasco, Johansson. And in particular, it's more powerful because this is the one that generalizes to loop level. So right now, there is no way to generalize the other two to loop level. So people are trying. Yeah, this I will not talk about at all. It is very interesting though. You rewrite your tree-level amplitudes as punctures on a sphere. The sphere lives in kinematic space. And then it's easy to see that they have some doubling structure. Okay. Okay. So good. So this is the KLT double copy. This is the amplitude of on the gravity or the double copied side. These are the single copy amplitudes A and AB. These, what you're summing over here are color ordering, so ordering of external states. And you end up with something that has no ordering of external states, permutation symmetric. So this is the 4-point example where this S over here takes this form. Okay, so S is known to all n, and it's a function of these orderings, alpha and beta. So when you choose at 4-point, you can just choose. So these are n-3 factorial orderings. So at 4-point, that's just 1. So if I choose that to be 1, 2, 3, 4, the S 1, 2, 3, 4, 1, 2, 3, 4 is US over T. Good.
I'm sorry.
Yeah.
So there are the alphas and betas are orderings.
Orderings.
And as a function of orderings, and you said that function just tells you which panels are there.
These, yeah, this factor over here.
Okay.
Yeah. Okay. So this here you can see is crucial to make sure that the amplitude on this side has the correct mass dimension to actually be gravity. So if it didn't exist, this wouldn't be gravity.
What did you say about 4 points that were how many orderings?
1.
Why?
So it's n-3 factorial is the number of orderings you sum over here. I'll explain a bit more why it's a smaller number than you'd expect. So over here, you'd expect n-1 factorial. Yeah, but it reduces for a particular reason.
In particular, the number of orderings for 4-point amplitudes is more than 1.
Exactly. Yeah, it's n-1 factorial, so 6. Yeah, 9, 6. Okay. This goes back to Ronak's question, which is why did I say something about the nonlinear sigma model, or here I've called it phi-PT, chiral perturbation theory, basically theory of pions. So yeah, so it's because when Yang-Mills is not the only thing that can be double copied. In fact, these 3 theories are also not the only thing you can double copy, but these are the simplest. And so I've written them in this table over here. And you see that you get other theories out, not just gravity. Gravity meaning dilaton gravity. Yeah, but gravity. Yeah, so you get some other theories as well. In particular, you'll recognize this one from our discussions before this, right? So Born-Enfeld is a double copy of Yang-Mills with NLSM or nonlinear sigma model. And yeah, so you just put it in over here, you put in the requisite amplitudes, and you get out the Born-Enfeld amplitude.
What is it? The final theory is for mesons in some particular position.
So I'm talking, so only the massless pions. I'm talking about like, yeah.
Massless, but the Goldstones live in both portions.
So good, they live, in this case, I'm thinking about them living in SUN cross SUN mod SUN.
Okay, so literally.
Yeah. Yeah.
And N is related to something about Yang.
Good. So actually, because the double copy kind of removes color, it doesn't matter what the ends are, whether they match up or anything
But
like
it
that.
matches between the Yang-Mills and the color.
No, it doesn't have to. Even that can be different. Yeah.
And who largely just
Okay. So
Okay,
a little bit, yes. I'll show you exactly at what point you use the fact that it might be larger. Yeah. Okay, so there are some extensions of this. This is just to say that it's not those 3 theories. It's not just massless theories. There's other stuff you can apply this to. Okay. Oh, so yeah, phi cubed is identity, and phi cubed is the bicolored phi cube. So phi is bi-adjoint, so it has two adjoint indices. So it's not just the regular phi cubed theory. And those bi-adjoint indices are exactly in the adjoint of this group and this group. That's what, that's what it is. Yeah. But yeah, it behaves as the identity, and more than that, inverse of these amplitudes actually tell you what this kernel is. Okay. Okay, so there are some questions already about why we only have one ordering at 4 point, or how many orderings you have, right? So so as I said, when you do the double copy, what you end up with is something that is permutation symmetric. So if you enforce the fact that it is indeed that the double copy formula is permutation symmetric, so this is one version of it where I've chosen the 1, 2, 3, 4 and the 1, 2, 4, 3 ordering. So it's a bit different than the previous slide. And now I just switch the positions around of the particles. I rewrite the same formula. I know that these two amplitudes have to be the same. So now I say that, okay, that means that the right-hand side has to be equal, which means that the LLSM amplitudes need to satisfy some condition. Yeah. Now, I mean, you don't have to take this that seriously. This is all to say that only special theories can be double copied. You can't double copy a generic theory. It has to satisfy some relations. These are typically called the BCJ relations. So, I mean, if you count the number of orderings at n point, it's n factorial, but traces are cyclic, so it's n minus 1 factorial. Now, if you're dealing with a theory that only involves FABC as the structure constant, is the only way that the color enters into the Lagrangian or the Feynman rule, then you get to n minus 2 factorial because of something called the Kleist-Coif relations, which is just a way of reducing those trace structures in a particular way so that actually you can get to a smaller basis of traces. So you're writing the amplitude as a sum over single traces times these partial and color ordered amplitudes. And if you know that the amplitudes come from only FABC type rules, then you can reduce those traces to a smaller basis.
Is this traces in the adjoint representative?
This is traces in the adjoint representative.
This only will work.
Yeah. Okay. It will only work for gluons. For other theories, there's a version of this that has to be true for them to be double copied.
Right.
Yeah.
So you're saying that if I take trace T1, T2, T3, T4, and the 6 different possible cyclic ordering, and I work in the adjoint basis, there's some identities.
It's not just that you're in the adjoint basis, it's that the thing that the full amplitude that you have only has FABC. So for example, it doesn't have a symmetrized trace over 4 generators, what they call DABCD. So it doesn't have a particular type of trace structure.
The 3-point functions came from operators.
Yes.
I see.
Exactly.
I see.
That if your Lagrangian depends only on structure constants, then you have this reduction automatically to n minus 2 factorial. If not, it's an extra condition you have to impose.
And this is something I can see by just writing out this thing.
Yeah, it's like some Fields identities or something. Yeah.
Okay. Even this area. Okay.
Okay. So now, and so in Yang-Mills or in NLSM, the non-trivial step is going from here to here, which happens because of linear relations that look like this, which are called the BCJ relations, which means that anything that can be double copied have to satisfy the BCJ relation.
And that this is true in Yang-Mills.
This is true in Yang-Mills at leading order. It's true for NLSM at leading order. It's true for the bi-adjoint scalar theory.
And there's some structural reason, or you just look at the outside?
There is some, I mean, if you try to generically solve these linear relations, those are the theories that come out, I guess is one way of saying it. Okay, so we'll. Okay. So in string theory, when I say leading order, I mean in the higher derivative expansion. So I kind of think, I'm thinking about what corrections high derivative corrections I can add, and whether I can use the double copy to say something about these high derivative corrections. So when I say leading order, I mean the Yang-Mills Lagrangian, not the Yang-Mills EFT.
And what is the more one?
In the string theory case, the original open closed duality, there it comes from monodromy relations between the open string integrals. And the alpha prime goes to zero, limit of that is just the BCJ relations. These NLSM amplitudes you can see as they have this theory called Z theory, which is like NLSM, except it has this sort of UV completed NLSM. And the alpha prime goes to zero, limit of that gives you NLSM. And so seeing that those integrals satisfy monodromy again reduces to these. But I don't know if that's a reason for you that they do. Yeah. Okay, so we'll focus on two aspects of the double copy. One is high derivative corrections, and the other is recursability. But there are other things you can talk about. I'm just not going to do that today. So they hold at higher loop. They hold at, the conjecture is that they hold to all loops for Yang-Mills at least. At the integrand level, not the integral. So integrand, you're still constructing integrands. It's been checked to very, I think 5 or 6, or maybe 7 loops, some large number of loops, and it still holds.
So then it works at the integrand level, then it automatically works at the integral level?
I think that's not clear.
Oh, sorry. It's just a very elementary question, but why can't you prove that by integrating prove that?
Because, okay. So one thing that is nice about the KLT formula, right, is that you're dealing with gauge invariant partial amplitudes. But the BCJ version, which is the one that goes to higher loop, is not a gauge invariant thing. So there's some gauge ambiguity in the way that you construct the. Sorry, is there a duster?
Oh, this is it.
Yeah, so you can write Yang-Mills, let's say just at 4 point. Okay, so this is the BCJ version of the double copy. It says that you can write the Yang-Mills amplitude in the following way. These C's are color factors, so they are just contractions of structure constants. So like CS would be the contraction that corresponds to this diagram with FABC contracted with CDE, right? T will be a different channel, etc. Now, because the Jacobi relation tells you that CS plus CU plus CT is 0. And then for Yang-Mills, you could find a representation of the amplitude such that NS plus NU plus NT is also 0. Okay, so these are the kinematic Jacobi identities. Now, this continues to be true at, so the conjecture is that for L loop, this continues to be true. D for L, I guess L. You still have this structure where you're summing over N's, C's over some propagators. And then the corresponding gravity amplitude, both at tree and loop level, is you take the color factors and replace them by kinematic factors. So you get this. Yeah. But these N's are not amplitudes. They are not partial amplitudes. So now once I do the integral, it's unclear what that formula looks like.
I was thinking about this switching relation, like this S, the third one here.
Yeah, so that
If that is true at integral level,
So this
yes,
is the loop level version of that is not quite known. Yeah, because this is the loop version of the double copy that is known. This is the analog of the BCJ relation over here. Yeah. So it's not known.
Because in general terms, I mean, there's mapping, there's those K in relation to the amount of string key, does it can even mystify the relation. I mean, the reason I'm asking is, okay, in string theory, typically there's a channel duality involved, right? You can look at a process in the open string or the closed string channel, but you have to sum very high states in the say open string channel, to get the gravitonic state. Like if you look at the energy between two people, and so on, right? And here it's a statement about Yang-Mills and gravity. So it's sort of kind of mysterious, right? And it's weird order.
Well, I mean, if you reduce, if you just look, if you look at the field theory limit, then and just the massless mode, so you take away everything else, then on the open string side, all you're left with is Yang-Mills, and on the gravity side, you're left with dilettante gravity. And so this is just a statement that once you do that alpha prime goes to zero limit, this is what you're left with. But the open string itself was special. I mean, it had some relations that it satisfied, monodromy relations. And the alpha prime goes to zero limit of those were just the BCJ relations. So there's some reduction as a result of that in the number of independent orderings.
But I mean, okay, you must go on. But I mean, does string theory tell you why the alpha prime going to zero limits must continue to a degree?
I mean, I'm not sure exactly. Yeah, I'm not sure. I mean, yeah.
So regarding that question, I think it's important that the PID relations do not involve a modular transformation. So the open string amplitude and the closed string amplitude are going in the same channel. That is why it's possible that they work in the map.
It's not it's not that. Yeah.
It's more like the CFT on a circle is like two parallel CFT on a line. Like two parallel CFT each of the lines that CFT on a line.
But even when channel dualities are involved, like the example of BFSS where they found this beat for 4 divided by 7. There was this modular form which said that lowest open string modes and the lowest closed string modes.
Even for modular,
Yeah, because it involves some modular language.
okay.
So that's how it worked for below 8 supersymmetries. This is kind of matrix given.
That's okay. That's very unobvious. I think this is much more obvious that it would work because you just
probably is more in line with what
right. Because in some sense you're just keeping the low line, the lowest massless mode. Yes, you can do that. Yeah.
Yeah, go ahead.
Okay, good. So let's just start with this understanding how high derivative corrections play with the double copy, right? So we'll still be talking about Born and Feld, but it's a bit loose. I mean, you can apply this to basically any other double copyable amplitude. Okay, so just because we were talking about helicity conservation, I want to point out that it's very unobvious from the point of view of the double copy, even at tree level or even in leading order, just because what you're double copying is Yang-Mills with nonlinear sigma model. And so Yang-Mills has a few sectors that have to vanish because of supersymmetry, but it's definitely not all. And nonlinear sigma model, the odd point amplitudes vanish, but at even point, it's still anyone's game. So yeah, I mean, it's not at all obvious from the point of view of the double copy why this.
What is the double copy again?
Yang-Mills with NLSM gives Born and Feld theory. Yeah.
You're not adding this
They are not BCJ compatible. Okay. So this is sort of the this is the logic is that we're going to look for color ordered amplitudes, which naturally will satisfy cyclicity and Christ-Queef relations, which are these FABC, basically saying that they come from FABCs. And we will, in addition, we will ask them to satisfy the BCJ relations, which at 4.8 is very simple form. Okay. Now you have some additional things that you want a healthy amplitude to satisfy. So if you have a, I mean, they have to be relabeling symmetric. So if I have, whether I'm calling this momentum 1 or momentum 2, it should still give me the same amplitude, basically. In addition, I want them to be local and unitary in the sense that I said before. So it needs to have poles at the correct locations, and it needs to factorize into lower point amplitudes, into real lower point amplitudes on those poles. Okay. So this is kind of what I mean by that. If you go on to, let's say, the S pole for a 4-point amplitude, it needs to look like a product of 2 3-point amplitudes. Now, these amplitudes for any Lorentz invariant theory are fixed, as long as I tell you what the helicities are. So as long as I allow only these, so no higher spin, no gravity type exchanges for my amplitudes, then all of the pole terms are determined. So, okay, so let's look at how this works for nonlinear sigma module of Carrel perturbation theory. So locality and BCJ say that I can't have any poles at t equals 0. Yeah.
Please tell me, I'm getting lost here. What are we trying to show? What are we trying to do?
We are trying to construct higher derivative corrections to two theories, both that are double copyable and two theories that are a result of the double copy. We just want to see how that procedure works.
Meaning you're going to change the theory.
I'm going to add higher derivative correction.
Okay, so you're going to change the theory that you're going to double copy.
Exactly. And I'll see what I'm allowed to double copy and what do I get out of it, and how restricting are both of these procedures.
And the things you're double copying in this example are this NLSM and Yang-Mills.
NLSM and Yang-Mills,
So
yeah.
see how NLSM and Yang-Mills can be changed.
Yeah.
And what you get out.
Yeah, precisely.
Okay.
Yeah. Okay. So in order for you to be double copyable. Yeah.
Why is that not necessary?
Well, so if you don't satisfy it, you won't get out a permutation symmetric theory. But in addition, if you
But you can sum more
you can do that, but you start running into some issues. So I mean, one thing is that you usually, okay, so something very non-trivial is happening. 1 second, let me just
now we are treating it as sort of another constraint of
yeah. So it just, even at 4-point, right? If you look at 4-point gravity, 1 2 3 4, this is US over T A 1 2 3 4 whole square. Okay. Now if you look at this factor, it's actually very carefully selected, because squaring this amplitude would give me a double pole in U, which needs to be cancelled, a double pole in S that needs to be cancelled. And in addition, if I want this to be a fully permutation symmetric theory, it needs to have a U pole, a S pole, and a T pole. But this is color ordered, so it only has U and S. So you have to add the T. Now, again, at 4-point, very easy to see. At higher point, it's much harder to see exactly how you can preserve that locality structure when you start multiplying amplitudes together. Yeah. And add that in with the fact that on a pole, it needs to look like a lower point amplitude of the same theory, right? These are all very non-trivial things. And it's, once you start pushing it a little bit, you find that actually there's not a lot you can do. Yeah.
But the range that I'm getting right is that amplitudes have poles and you square them, you get double.
Yes.
Unless something
very special is happening to the prefactor sitting out in front. Yeah. The double copy automatically satisfies it, but it's not very obvious from that construction why it should satisfy it. Yeah, but obviously, like if you do the calculation, you'll find that everything vanishes that is supposed to vanish. Everything that is not supposed to be non-zero is non-zero. Everything agrees, both these constructions. Yeah, they don't vanish. Exactly. So it's like a sum of terms that vanishes in the end when you do that sum, but the individual things that you're adding together are definitely non-vanishing. Okay. So if you're looking at the nonlinear sigma model, you now say that, okay, now I need to satisfy locality and BCJ relations. And this says that I can't get a simple pole at T. Unitarity and soft behavior then say, actually, you can't get any simple poles. Okay, because there are no 3-point amplitudes in a theory, in a SUN, cross SUN, mod SUN type coset model. So if you don't have 3-point amplitudes to factorize into, then your 4-point amplitude can't have poles. So now my job becomes much simpler. I just need to write down these local polynomials of S and T to all orders.
Because that locality, this BCJ is no simple pole amplitude.
Yeah. So this is it's a very similar argument to the one we made over here. It's just you have to track when I'm allowed to or not allowed to have a pole, and you say that, and basically you find that if you have a T pole, then the BCJ relation will tell you that the other ordered amplitude will have to have a double pole in T. So then you can't have a T pole. Yeah. So it's very similar to this type of argument. Yeah. Good. So
these are simple poles in a particular order.
That's right, in this one. Yeah. Yeah. Obviously, once you do the relabeling, you'll have a simple pole in T, you won't have one in S or whatever, depending on which relabeling you did. Yeah, okay. So you place all these constraints and you get this answer over here. Where this
soft behavior, by extension, tell you that there is
yeah, actually, there was no reason to use the soft behavior. The reason I said soft behavior is because in a generic coset sigma model, you don't get soft behavior. It's only in a particular coset sigma model. So if you but saying that you have soft behavior says that it's a non-generic coset, and then it doesn't have 3-point amplitudes, and then unitarity. So it's a bit, yeah, but I agree. For this coset model, you don't have 3-point amplitudes. You have soft behavior, so you don't have. It's not an extra constraint. Yeah. So yeah, okay. So you have this one fitting out in front. That's what we're used to seeing as the NLSM amplitude. It can. So if you have, I mean, in principle, it can. Yeah. So. So this is a BCJ relation. No, yeah. So the first line or the second line? Yeah. So you don't have 3-point vertices, so then you can't have poles. Yeah. Okay. Good. So now we can do this for Yang-Mills.
How much of this will follow without BCJ?
Without BCJ?
Yes.
Without BCJ.
Anyway.
This part is true, but exactly the form of these corrections, I mean, there is no reason for you to have S square plus T square plus U square. You could have S square plus U square, different coefficient, T square.
Sorry, is it different coefficient?
There are two terms, for example, at this order. Yeah.
This is just for the color.
Yeah. Another thing to notice is that there is no 1 over lambda square over here. And that goes away because of BCJ.
Right. So, okay, so you're getting a permutation in variant amplitude.
That multiplies T.
That multiplies.
Yeah, this is specific to 4 dimensions. Sorry, this is specific to 4 point. At 6 point, you get more structure. It's not just the T times permutation.
Right, and then this is really crucially BCJ, because BCJ was the statement that up to some S new factors it's permutation. Right now.
Yeah, good. So, all right. So now,
it's sort of like made it like a scalar amplitude.
yeah, but it was always a scalar amplitude.
Sorry, the scalar, I mean, no extra indices, no extra other factors.
Yeah, except for the bit that sits out in front of it.
But that, right.
Yeah. Again, this is very specific to 4 point. This kind of something times permutation doesn't quite work beyond.
Okay.
Yeah. Okay, so for Yang-Mills, you have to be a bit more careful because you have helicities. So, yeah.
Now, we could write down a chiral Lagrange, and we could write out terms as 1 by lambda.
Yeah.
There's a particular chiral Lagrange that has this structure, you're saying?
Yeah.
So you have to choose that.
Yes.
Okay, fine.
Yeah, that's right. But this is a subset of that.
Is it just one?
Yeah,
I don't know.
Yeah, yeah.
Just permutation symmetric stuff.
at 4 point.
Yeah.
At 6 point, it's slightly
But the chiral
it's a bit
Lagrange
different.
curve for QCD would not have this.
That's right. Yeah, so we'll see that for Yang-Mills, it will be slightly different. So for Yang-Mills, one thing that changes is that the relabeling now you have 2 different plus, minus, minus. There's also plus, minus. So in principle, they are different functions.
The actual pion Lagrange.
Oh, I see.
The one you get in the real world.
Yeah.
This is some generic chiral Lagrange. There's no reason to look at this. This is right.
It will match at leading order. At
Meaning the T.
T to all n. All n point. Yeah.
That's some sort of behavior.
Yeah.
Even the coefficients of the higher derivative terms are least taken here, right? Because they're all stable.
Yeah.
Because,
So this is actually something we're looking at now, which is what happens beyond 6 point and beyond, and how much BCJ actually constrains things. And it seems that, okay, I don't want to say anything, but it's still, people are still thinking about it. Okay, so you have, so for Yang-Mills, you repeat the same procedure, right? And then here, now you do have genuine pole terms because you're allowed to have, 3-point interaction. In particular here, this is the vertex that you were asking about, Abhijit, which is that you have a F cubed, so you have a plus, minus. There, you have a plus vertex that comes from F cubed. It also gives you a plus, minus, but yeah, it gives you plus.
Double copying only for 4 dimensions?
No,
So when you working in 4 dimensions, just
convenience. Yeah,
everything gives a to work.
yeah. That's just convenience. Basically, I like using spinor helicity, so I often default to 4 dimensions, but there's no reason to do that. Well, we live in 4 dimensions. That's a good reason, but yeah.
I personally, when I see bracket 3, 4, I don't know why. It still doesn't matter.
Okay. I mean, it's some kinematic object. Yeah, that has a little group weight of a positive helicity particle. Yeah. Okay. Okay, good. So you have all these poles that now appear in your Yang-Mills amplitude because you have allowed for these kinds of high derivative F cubed interactions. Okay. Necessarily, when you're doing the double copy and you get the Born-Enfeld, you expect these all to vanish. It's very non-trivial that this will happen in terms of just thinking about, okay, you're taking something with poles and it's multiplying something and long sum and you get something out and you'd expect.
You're not getting double poles, you're not getting poles.
Yeah, exactly. So you then can do this double copy and you can get all the Born-Enfeld amplitudes out and none of them have poles. Yeah, so it's kind of magical that this works. And yeah, and it works beyond 4 point as well. this procedure. So you can kind of, it's very nice how locality is so built in to the way that you define KLT, even with higher derivatives. Yeah, so instead if over here I put in the like Veneziano amplitude or something, it would be fine. I mean, it wouldn't be SU over T. It would be the full string theory KLT kernel. Yeah, but yeah, it would work.
Sorry.
So
So the left hand side, you compute the 4-point amplitude and 400.
yeah,
Because that's for the abelian theory. Right?
that is an abelian theory.
And when you say equal to, just say, then you take Yang-Mills color perturbation theory double copy.
Yeah.
And okay, good, and color or whatever symmetrize, and
Yeah.
then you get exact equivalence with Born and Feld.
Yeah.
Provided some terms are chosen for the higher derivatives. But so far, no higher derivatives, right?
So all of these are higher derivatives.
Those are higher, right?
Yeah.
Again,
I mean, already here, right, for Born and Feld leading order, this would vanish. This is all plus. That's why this is a high derivative term.
So you changed the angles and added high derivatives. Yeah.
This is the Yang-Mills with higher derivatives.
And but then what was your A0, A4, A6?
So these, okay, some of these are fixed, right? So this A0 is just G, Yang-Mills coupling. These are related to GF cubed.
GF cube, F cube, or G? Oh.
Yeah, F cubed in the Lagrangian, GF cubed.
Oh, so this would automatically. Wait, this would automatically come out of, if it's related to what comes with the F cube, which if it's the whole contribution, it should be automatic. Why is there a lambda to the whole? So I'm going to say.
So, okay, I mean, depends on what you're calling GF cubed. I like to keep these dimensionless so that I can count dimension easily. So I just made it, I've just removed all the dimensionality into these lambdas. Well, lambda is like some EFT parameter.
Yeah, this is very elementary. I can understand that poles in a 4-point function are related to 3-point function.
Yeah.
But in Yang-Mills, those poles will not come with some suppressed.
They don't. That's this. That's G Yang-Mills.
Okay.
Now, if I have a GF cubed is dimension full.
Now you change the.
Yeah, it's dimension full. But then when I'm using these B's and C's and all of these are all dimensionless, I pulled out the dimension in lambda.
So you're adding terms to your Lagrangian.
Yeah.
And those are coefficients of terms.
Yeah, and these are the most generic terms that I can add, which are compatible with BCJ, locality, unitarity.
Okay, but in order to get Born and Feld,
yeah,
you will have to make some particular choices for these terms.
Not at leading order. Yeah, so this is a way. So Born and Feld already happens at leading order. This one over here is Born and Feld.
So that way it gives Born and Feld.
Yeah, yeah.
So that's opening sentence is true without any higher derivative.
Yeah, exactly. So that is just this. And now this is a way of defining what is Born and Feld beyond the leading order. Because I have corrected Yang-Mills, I corrected Chi-PT, and now this is a way of saying these are the higher derivative corrections of Born and Feld, treating it in a very effective field theory sense, where I'm saying that what is it that tells me what higher derivative terms to add in my EFT? It is the fact that it is a double copy.
Okay, so yeah. Suppose I look at just on the point of view of Born and Feld, what is better about adding these higher derivative terms than anything?
That's unclear. That even in gravity is unclear.
Okay, so it's just a set of terms that come because you can double copy them.
But the point is that you can double copy them and you still respect locality and you still respect factorization even beyond the leading order.
But say I didn't care about double copy.
Yeah.
From just I was just a Born and Feld.
Yeah.
I added a term that was not one.
Yeah.
Would something go wrong or?
So basically the question you're asking is?
Born and Feld.
Yeah. So the question you're asking is there anything special about what terms the double copy picks out in terms of higher derivatives? And it's at the moment, it's not clear to me that is there some symmetry reason why these are the terms that need to exist or not?
But one thing that you're saying that hasn't been clear to me as well, not every term that you can add to the Born and Feld
That's right.
is double copy.
Yes.
And is that also true in gravity? Not every term you can add to the gravity vector is double copy.
Yeah.
Okay.
For higher derivative.
Comes from an
Yeah. For higher derivative correction.
For higher derivative. Okay,
specifically.
the terms that come in the string theory effective action.
All exist. I mean, they'll all come
If you
from
take the whole.
the full
thing.
thing. Yeah.
But if I just take the terms and changed coefficients, it would not. Sorry.
No, sorry. If you wanted general coefficients, but the same structure of the string theory in the low energy, you would get it.
What do you mean same structure?
So it's like say it was, I mean, when you take the low energy limit of string theory, it connects the n point to the n plus 2 point to the n plus 4 point coefficient. Or the I don't know, this 4 derivative term to the 6 derivative term to the 8 derivative term, not with the most general coefficient sitting out.
Yeah, there's some particular.
But you can, yeah, but you can replace those by general coefficients and you'll still get, you get this, that will work. But there are terms that don't appear in the low energy limit. So those you won't get.
Let me just ask, sorry, you know, other coefficients you get in string various directions with one and double or
These, yeah, so these are those are specific values of these.
and you don't get.
No.
That's kind of interesting. Is it, and is there a KLT type of understanding?
Not in my, I mean, it involves, it depends on exactly what you mean by KLT.
Okay.
But it depends on what exactly you mean by KLT. But as I said, there is some, there is an amplitude called the Z theory amplitude or Z theory amplitude that has, whose alpha prime goes to 0 limit is the NLSR. So KLTing these two will give you some amplitude again, which reduces to this, and the alpha prime goes to 0 limit. But this matches the open string effective action, as long as I choose the Wilson coefficients to have some values. If that, so yes, I mean.
Does it also give you more than that?
It gives you more than that. Yeah.
It doesn't give you this back.
Yeah, exactly. Exactly. Good. So
does it give you those, you added some, you said that you wanted to add something to
so no, it doesn't, but I'm not entirely sure whether we should read too much into that, because there you chose a way of regularizing, and it's unclear whether that is double copy compatible or not. It's like it's like choosing a supersymmetric regulator or not, right? So is that compatible with the double copy? It's unclear. So then if I, yeah. So
let's go back.
These, I mean, if you choose the Wilson coefficients in some way, then they will be. So all you're saying is, I want to choose B. I mean, basically anything that appears in this line to be 0, anything that appears in this line to be 0. You can do that. Yeah. Yeah.
So then it seems like you're saying that you use the coefficient in such a way that you can get the string theory effective action. You can also use the coefficient in such a way that you can preserve the duality behind, which is not the string theory effective action, but then
I mean, they're the same. So I mean, so for setting, so if you take the string theory low energy effective action, all of these are 0, all of these are 0, and these are fixed to be, these A's are fixed to be some values.
So I thought earlier you made
That's the loop correction. So when you do a loop, so I don't know what happens when you do a honest to God string loop calculation. Yeah, but if you're looking at just this counter term analysis, everything makes sense. Yeah. Yeah.
That's what's confusing me about your language solution, which is, of course, the string theory answer can be reduced to the effective action. Right? That's a given.
That comes from the double copy. That's the part that's not the given.
But, let me just make sure. Let me make sure that I understand what I mean by not using the word Wilson coefficients. And effect, I compute an amplitude, honest luminous and string theory. I take the low energy limit. Okay, leading order is what I get. I should have explained from the Born interaction.
Yeah.
Then you have corrections.
Yeah.
Right?
Yeah.
Are all those corrections of the type which you would get again for a scattering amplitude, not in the effective regard, from a theory which admits always a double?
That's what we find. Yes.
Okay.
That is what we find.
Yeah,
that is what we find. That is.
there's no,
Yeah.
no, there's a some explanation just from the internal stuff. Of course, I know with this motivation you forget it, but the corresponding gravity statement you're coming to perhaps is.
Yeah, that is, I'm not coming to it, but it is true.
It is true.
But that is scale, that's scale, right?
That is scale.
That's like full string theory.
Oh, so, yeah, that is KIT.
Yes,
There's some understanding why.
yeah.
Yeah, there is, here it's a bit looser because what that KPT is in the high energy is a bit harder to see. There is a low energy open string effective action, which is at leading order the square root. It's known at 4 point to quite a few orders in this paper by Dixon and Broidel.
I'm spacing out when you ask the question.
No, I was just asking whether there is some, the way we talk about string theory corrections to blue ionic amplitude, gravitational amplitude, is there is something for Gordon paired?
It's not just 4 gluons on one plane.
No, but this is more than
Yeah, the low energy action has been written down.
No, I mean, look, the full scattering happening, the 4 gluons happening. Listen, here, I mean, Veneziano.
For Yang-Mills, yeah, for colored.
One.
Yeah, even for.
no,
I don't know if I'd call them blue
I
ones.
mean, the lower limit of Venezian amplitude would give you.
If you take the lower, this amplitude I'm talking about, for any number of gluons, keep the leading low derivative term. That will be reproduced from one.
Yeah.
Because Bodenfeld has F to the end, and all the corrections that it's not keeping is higher derivatives of it.
Yeah.
So it is a different way of computing the.
Yeah, it's keeping all the lowest order of all number factors.
From Venezian amplitude, you can just get this.
But it's not that it's n point minutes.
10.10.
Yeah.
Yeah.
The lowest order, keep the lowest order of all of those. It basically is the same as one.
Yeah. Here I'm talking about 4 point just to show you the simplest. I mean, because the formula actually fit on a slide. You could do it to n point.
Now, there is some, so let's say you require this first equation hold in the string theory. Okay, so there is some Gordon paired coming from string theory, and then there is this Yang-Mills that is coming from string theory, and that chi-pt is something that you require, right? Some combination with chi-pt.
Yeah.
Does that also come from string theory? Is
No,
that from string theory?
No, but there is a so you can take the sample. There is an object I can give you that involves alpha prime. That when I use the string KLT kernel, and I will get this equivalence. Yeah, I don't know what to call it. It's called Z theory. It's called Z theory, abelian Z theory. Yeah, but I don't know if it's actually a theory, and in the sense of can you write down a Lagrangian? How local is it? What are the properties of that are? I have not studied exactly, but that extension with alpha prime exists, some finite alpha prime.
Can I also ask a question for some string throughout the Python theory, which will multiply with the Venezian amplitude gives Venezian amplitude?
Yeah.
There is some sort of object.
Again, I don't know whether you would call that a theory. Has a bunch of very not nice poles. And so I don't know if you would want to call it a theory. There is a finite alpha prime kinematic object I can give you and say that is, yeah.
So just to make sure, there seem to be two miracles here, if I understand. One is that the higher derivative corrections to bond and fill in scattering amplitudes that you contain in string theory are of the type which are double copiable, regardless of what those copies are.
Exactly.
Right? But number two, at least for the Yang-Mills part, let's say I can understand maybe some Z theory. Actually, the double copy itself, each of those terms in the double copy have their higher derivative corrections as they come out. Is that
Yes.
right?
Yeah.
I thought that's what. So Yang-Mills,
Yeah.
Yang-Mills corrections are those for many iterations.
Yeah.
So to get the string theory,
A larger class, I mean, you have to choose the Wilson coefficients to have some values for it to match exactly.
But this is what I was also trying to understand. We know what we want from string theory on the right hand side. And the right hand side being quadratic.
Yes.
We know what we get from string theory
Yeah.
for n variables,
Yeah.
n degree
Yeah.
If I choose those coefficients for the n degree so with those numbers,
Yeah.
and some choice for this chi p,
And then you get the right numbers out.
then we get it.
Yeah.
Amazing. It's
Yeah. You get the right numbers
The
out.
angles is chosen to be.
string theory.
String theory. String theory when alpha prime goes to zero.
Yeah, so that's completely
This is
flexible.
your point, yeah.
In the field theory limit.
What do you mean in the field theory?
As a alpha prime expansion.
Expand it, but all of it.
I mean, we check to some finite number of orders.
Oh, no, generally.
No, not as far as I know, unless, I mean, I guess it depends on how much you want to believe this Z theory argument.
But you said you can give me a finite alpha prime.
At 4 point.
Yeah.
Yeah, but beyond that, they don't have a argument, whereas we check that this actually works at 6 point as well. 5 point and 6 point. Okay. Okay. So, okay, so we kind of already talked a lot about these corrections. I just wanted to mention that, you know, there are other things you can try and do, and this is related to sort of few things we already talked about, which is how much can you mess with this procedure, right? And people have tried quite a bit to mess with the procedure because you want to expand this as much as possible because otherwise you're just stuck with this small class of theory, right? And it does.
In higher derivative corrections, you said at tree level, this was the answer. Right? Even at the loop level, what happens to this was the one loop correction to
Yeah, so actually these other double copies, the ones that are not gravity, haven't been checked a lot beyond tree level. We did a very preliminary calculation, which is a 4.1 loop, and it seems to work. Like if you take the 4.1 loop double copy to construct Born-Infeld at one loop, it gives you the correct answer.
The correct answer being the one that satisfies.
The same answer that I showed you before. Yeah, but that was a very, again, preliminary, just 4.1 loop. Yeah, and yeah, but it's not been studied a lot actually. This one loop for the other double copies that are not just gravity.
And that is not what you get from string.
That is, I mean, that particular counter term you mean? Yeah, it's not there in the open string.
But is it the statement that you can also get what you get from string theory one loop with a different choice?
Sorry, say again.
So I thought at one loop you would have two of them. You had one correction that you wrote down, give you n duality. Right? But if you didn't add that correction, you could also have just computed what you got from string theory.
Yeah, and that
and that's a different answer.
That's a different answer.
So I'm just wondering if the double copy at one loop can give you both, depending on the choice.
It can only give you the open string. Yeah, which is also then suggesting that the way that you're doing the integral is not double copy compatible, because even though you're using the double copy to find the amplitude, it's anyway, that's a bit like, yeah, that becomes a question of interpretation a little bit, so I don't want to say too much. Okay, so all right, so
sorry, just to say, it seems to me the very early interesting question is what is special about the theory intrinsic that can be built over?
Yeah.
You know, we can find some physical thing that's special about it.
I fully agree. I think this is a very interesting question. It's a very strange question to ask for the simple reason that I mean, how else do you do it except you just construct a bunch of stuff and try and look for a property that it satisfies? Yeah. It's not, I mean, yeah, it's a bit like you're fishing in the dark for a property.
Yeah, maybe you have a guess.
Exactly. So if you have a guess for a property, then you can check whether that's true, but I don't have a good guess for the property. All the easy ones that you might think about, locality, soft behavior, supersymmetry, are just very automatic in the double copy, and so then it's like that doesn't help you.
Since this works order by order in some expansion, it can't even be good ratio.
Yeah.
So that'll be fine.
Well, I guess, so there is one question still here, which is, say you restricted all of your coefficients in both these theories to lie in like the EFT heathen. So to satisfy some positivity constraints, does that immediately put this in that same like EFT sense? So it's like, so that's saying that your high energy, that it's unitarizable or whatever at high energy. So
This is regular behavior, large S fixed T.
it is large S fixed T. It needs to look like it has some exchanges of some higher mass particles. So if you say that, and I don't know the answer to this question, but if you say that the coefficients here satisfy the correct positivity constraints and the coefficients here do the coefficients. Yeah, the dispersion. Yeah, exactly. So I didn't make this term up.
Okay.
This is Niwa Arkani Hamed and Yutin Huang. Yeah. Yeah. So okay. Those are inequality times things, but I agree. But I mean, that gives you inequalities. The question is, if you satisfy inequalities here, can you see that you have to satisfy inequalities here? It's very unclear. I mean, I don't think anyone's done this calculation. I think it's a calculation that's waiting to be done.
Question I'm wondering. I mean, if you are trying to ask what kinds of units calculations, let's say, by adding higher derivative terms, admit double. But strictly speaking, I guess you want to ask it up to some movement. I mean, because it's an effective theory beyond the point, right?
Yeah.
So it's not a, I mean, in a finite theory, of course, it's completely opposed or in a renormalizing theory. Otherwise, maybe you find it.
I was wondering whether something like this might be true, that at any given derivative order, you will typically have a particular AJC. Like you take large S fixed T.
Yeah.
But these guys are ones that give softer behavior than something like some.
Yeah. It's possible. I haven't thought about it.
It's probably wrong. Just to give an example.
Yeah. But
If you want then further question, right? You were talking about this left hand side, that one that you construct after you put these together, right? But you could ask even the ingredients.
yeah.
She made them satisfy from BCJ. What are those?
Yeah, whether those select some good behavior. Yeah.
And just in the English one, but just in is and working only at tree level, you have this electromagnetic duality. And was that something that translated this symmetry into or not?
I guess you could think of them as, so it would say something like, you take a bunch of Yang-Mills amplitudes, dressed with some scalar polynomial, rational function, and that gives you 0 when you sum over it. Yeah, I don't know whether you want to call it a symmetry, what you want to call it, but yeah.
Is there a way to understand this material left side from the right side?
Not as far as I know, no. It's very unclear to me where it comes from.
Should people to map the action of the
Yeah, so this is what I said. I mean, it boils down to some relation between Yang-Mills amplitudes, and it's very unclear to me why that relation has to be satisfied. Yeah. Okay. So also the relations are only satisfied by certain Yang-Mills helicity configurations. So it's a very strange. I'm not sure how to interpret those. Okay. So not all, yeah, like the split helicity ones will not give you something 0 because Born-Feld doesn't vanish for split helicity. So it's only the unequal helicity combinations that satisfy some relation for Yang-Mills that sets the Born-Feld to 0. So it's very hard to see from the point of this formula. Not at 4 point, but at 6 point and higher. Okay. So the other example that I wanted to sort of discuss, I think it will be not very long. I know I've been talking for a while. People are looking a bit tired. But this will just be a question of, we already looked at.
So the evidence, I'm trying to get in my mind the evidence that something good is happening. Okay, so first of all, Yang-Mills double copies to Einstein.
Yeah.
Then string theory, open strings double copy to pure strings, and Born-Infeld is double copy.
The other way around. You can write Born-Infeld as a double copy. Yeah.
Yeah. Okay.
Yeah.
These are the three striking statements.
Yeah. You can also do NLSM with itself. That gives you.
Let's say I don't care about the special NLSM. It doesn't appear a string there.
Fine.
Yeah.
Yeah.
What do you get? The kind of TV system?
You get something called the special Galilean theory. It's a theory of scalars that shows up in some scenarios. Nice. It has some nice properties. Yeah. Okay. Okay. So good. So this is like the last part of the talk, which is just to see or note that there is a relation, or there is a relationship between theories that appear in the double copy and recursion relations. So every single theory that appears in the double copy, there's some way to recurse it. Okay.
Which generally means that is good predictive.
Which, yeah, or I mean, not always. Here, these are EFTs. They don't. Yeah.
So the BCFW one.
The BCFW ones do. And okay, so this is sort of just an excuse to set up the last lecture. I will admit. So it's just like, let's understand BCFW recursion relations because we're going to need them in the next talk. But what its relation to the double copy is the following, that BCFW behavior is somewhat easier to see in Yang-Mills, and in gravity, you should see this paper. It's like, it really goes hard with the Feynman diagrams trying to figure out exactly what the BCFW scaling is. But I just want to say that with KLT, very easy to see that Yang-Mills BCFW implies gravity BCFW. So that's where we're going. Okay. So what is BCFW? So this is a recursion relation that was introduced by Brito, Cacciazzo, Feng, and Witten. And it's very similar to the one that we saw a couple of days ago. So you start with, you start by taking your external kinematic data, P, and shifting it by introducing some Z parameter, complex parameter. These lambdas or square brackets, lambda tilde is a square bracket, lambda is angle bracket. And these are just, this is just in 4 dimensions. I can split up my momenta in this way if it's massless, right? So I'm going to choose 2 legs, I and J, and I'm going to introduce this parameter Z in the following way. Okay. Okay. This is nice because
It's square in terms of lambda tilde square, lambda square, and epsilon by square.
sorry,
Suppose I have the vector square, P mu square.
P mu square
I want to
is
know what
0.
I know, but I want to know what, as an algebraic thing, what I have to do with this thing.
I would have to
Bracket, square,
angle.
Square, square, meaning lambda tilde contracted with lambda tilde and lambda contracted with lambda.
Yeah.
Okay, and why is that?
It's trace P sigma.
Oh, it's 0 because you're contracting equal. So because
Because epsilon, it's an epsilon tensor contraction.
Oh, so this construction guarantees squares.
Good. Yeah, it guarantees that P square is 0. It also makes it easy to see what the little group is. So little group should leave. It should leave this invariant.
And just let me do some counting of data there. So there are 2 lambdas are complex.
Yes.
So
They're complex if P is complex. I mean, no, they're complex regardless of whether P is complex.
okay.
Yeah.
So at the moment, I'm thinking of lambdas and each lambda is 2 complex numbers.
Yeah.
So there are 4 complex numbers in lambda tilde.
Yeah.
Now clearly I can rescale lambda and rescale lambda tilde the other way around to get rid of 1 complex number. So now I have 3 complex numbers here.
Yes.
Oh, and and how is the data line? So I'm sure.
And you have, so with P as well, you have one mass shell condition.
Yeah, so that's
So 3.
3 real numbers. Oh, but now you're saying that made it up. So that's
Yeah. Okay.
This shift, what does that do to the moment?
So it does the same thing to the momentum. So you can write it as Pi goes to Pi plus Z times some R or Q, whatever you want to call it, some other momentum. And similarly over here, you can do Pj goes to Pj minus Z times Qi. So then Qi and Qj will be given by some combination of these spinors. There's a way to just write this, which I think that's what you're asking. There's a way to just write this in terms of the momenta and not the spinors.
In the square bracket with the plus that shift.
Yeah.
The angle bracket with the minus.
Yeah.
The P is both, right? There is a quadratic piece also. Z square piece.
No, so if I look at the Pi momentum, it will be square I with angle I, and angle I is not shifted. So it's just a linear shift, right?
Oh, so I and J are a subset.
I and J are just two particular legs that I have chosen.
Oh, I see.
I and J, and I'm doing this shift. Yeah. So for I, I'm only shifting the square. For J, I'm only shifting the angle. Yeah. So it's linear shift for just two. No, just for two, I and J. Yeah.
And what is the polarization vector for the plus polarization?
It is it requires some auxiliary spinors. Yeah, so it's like I sigma mu auxiliary object. I would be epsilon minus mu.
So
Maybe there's some minus sign or I or square root 2, maybe. Some like normalization exists.
psi is a spinor.
It's a spinor. You can choose it to be anything. Your final amplitude won't depend on it.
So the first line, the I guy is shifted by something, but that is J.
Yeah.
The same J there.
Yes. Yeah. Yeah. This is, if you don't choose it to be like this, you won't satisfy momentum conservation. Yeah. So this satisfies on shellness.
Shifted by plus Z, J.
No, because it's not PJ exactly, right? Because it's like
something, but it's fixed.
Yeah.
Roster. Yeah.
yeah, it's not it's not PJ.
It's not that.
Yeah.
But it's a mix of Pi and J. Because it's only
It's a mixture of angle I and square J. I don't know if you can say that is a mix of Pi and PJ.
Like a information in lambda and lambda till gas.
I mean, it's some combination, right? It's like P0 minus or plus or something. Like, I mean, it's not you can't covariantly write it. Yeah. Okay. All right. So good. So now we want to play a similar game as we did with the 3D recursion relations, right? We know that when will there be poles in Z? There will be poles when intermediate momenta go on shell. Okay. All the momenta are okay. So if these two I and J lie on the same side of the factorization channel, then the intermediate momenta doesn't depend on Z. So you don't get a pole in Z. So you need them to be on opposite sides. And in that case, there is a single pole that you pick up. Okay. So you get some structure like this. You have a pole at 0 that I've introduced, that I have not introduced. It's AN at 0 is the physical amplitude, dz over z AN. Some factor of 2 pi I. Yeah. So, okay. And so this is exactly the same as we did before. You get pi squared looks like this. So you sit on the residue and you get a factorization into lower point amplitudes. Okay. Now, of course, this is the non-trivial part that Yang-Mills, the residue vanishes at z equals infinity. But I already showed you yesterday that Yang-Mills actually is very, the way that the stuff that amplitude scale, etc., it's actually very easy to show that that residues vanish at z equals infinity for Yang.
Is this the same as the edge scaling property or is something?
It is the same as it being renormalizable. Renormalizable.
Renormalized. So not edges. It's like all derivative.
It is, yeah.
It's not S fixed. It's just.
It's not S at fixed t, but it is definitely basically probing in a particular direction high momentum.
I see.
Yeah.
But as you say, it's just what dimension is the complex?
Roughly. Yeah.
Okay.
Yeah. Okay. So note that this sum over diagrams is very dependent on which I and j I choose. Right? So in particular, in Yang-Mills, if I choose I and j to be.
But we just make only two of them very good fast, right?
Yes.
Because so that there are scale both S and T.
Oh, good point. It sounds like scaling just S.
Yeah.
In a 4-point amplitude.
So one guy is just going to 4.
I guess that depends on, it can scale. So you need them to sit on opposite sides of the thing. So if it's, let's say you choose 1 and 2, S is unshifted, T is shifted, and U is shifted. Yeah. So it depends on which legs you choose to shift, but you can make S and T. You can make S and T go to infinity.
Right,
Yeah.
right, sure.
Yeah.
Two will shift, but not the.
Yeah. Okay.
Right. I mean, it's basically forward scaling.
Yeah.
Because you go to very high Z, one guy is another guy.
Yeah. That is the limit when Z goes in.
Right.
Yeah. That is what you want to. I mean, once you show that vanishes, then you're good to go. Yeah. But okay, sorry. You have to have an argument at every endpoint that term vanishes before you can use the construction to construct the endpoint amplitude. So if you have to construct the amplitude in order to show that it vanishes, that defeats the purpose, right? So you need a mod. Yeah. Okay. Good. So there's this choice of what particles I'm shifting, and if they're adjacent, then I get 1 over Z, and if it's non-adjacent, I get better behavior 1 over Z squared at infinity.
And you pull the epsilon parts out of the amplitude.
The polarizations? No.
So this grows so slowly, even with the polarization.
Yes, but as long as I choose appropriately which one is a positive and which one is a negative helicity particle. So I haven't, I mean, the full amplitude with the polarizations, but I've chosen it so that if it's a minus particle, I'm shifting the square of this guy. If it's a plus particle, I'm shifting the angle.
This sounds very low behavior. I mean, 1 over Z sounds like it decays with energy. And can you give us an intuition for why that happens? For instance, in gravity, typically things grow with energy.
So gravity, I'll show you why. This is just Yang-Mills.
Okay, but even in Yang-Mills, you'd expect constant design.
I mean, why?
But
No, because then you'd pick up, if the integrand is 1 over Z, you pick up a Z equals infinity pole. So this is just the amplitude, and then it's times 1 over Z. So the integrand is 1 over Z square. So you don't have a pole at infinity. Yeah.
So pairing the polarization in such a way that it's almost orthogonal or something like that.
No, I'm just saying that so I know that there is some minus polarization, right? For an external minus, there's a minus polarization. And I know that the minus polarization is going to come with an angle on top and a square at the bottom. So I don't want to do the shift for this particle I that shifts the angle. I want to do it so that it shifts the square. So actually this gives me a 1 over Z, where it normally could have given me a Z. Yeah. And similarly for the J. So I do that so that I don't pick up that extra factor of Z.
Anyway, okay, this helicity business, P and epsilon, you could do this in high dimensions.
Yeah, you could.
So, because of my inability to understand.
So yeah, so I think the Young-Mills argument in higher dimensions goes as you have to. There is a way of building. Yeah, actually, I only know it in a supersymmetric sense.
We can talk about it.
Yeah.
Just want to try to understand why this you have this very rapid decay. Right?
You can show it from some like Feynman diagram.
I'm sure it's true.
Yeah.
I'm just trying to understand.
Why? I mean it's some like mass dimension, but also you have to be careful about exactly what mass dimension.
So
So
organizations are very important.
they do because so the mass dimension itself is 0, let's say,
Exactly.
right? Or actually it's 4 minus n, right?
Yeah.
So if I did a all line shift,
Yes.
I would get 4 minus n.
Yes.
Except that I also have polarization tensors.
Yes.
So I can actually get a better behavior for an all-line shift by choosing things so that because I know that I'm going to have some external little group factor that scales in this way. So I can counteract that.
This is what I first thought. I thought you were going to say that it's the coefficient of that little group factor.
Yeah.
But that's not what you're saying, right?
No, so here when I say adjacent shift, I do have in mind some particular helicities that I'm shifting the angle and square of. If I did it differently, you're completely correct. There would be a times z square or something
Right.
like that.
I'll ask you later.
Yeah. So, okay. So in particular, the MHV sector is very simple when you do BCFW because you get only one term when you shift 1 and n. So say this is the amplitude I want to calculate, plus, and 1 and 2 are the only negative helicity particles, right? So this is Young-Mills, MHV, maximum helicity violation. So, okay. Here now let me choose n and 1 to shift. Okay.
Just one last question. Are you increasing P in the direction so that its dot product with epsilon is not large?
So P dot epsilon is always 0.
No, P1 epsilon.
Ah,
I mean, I was imagining there's a factor of P1 epsilon 2 times P2 epsilon 1 or something like that in the denominator, and then you're making sure that those shifts keep that small. Is that something like in the numerators?
so maybe let's talk about this afterwards because I think it's not very. I think it's probably true what you're saying, but I would have to just write down the dot product in my head. It's not very clear. Yeah. I think actually this is in Henrietta's textbook, so I feel like I really should have known it off the top of my head. My advisor would be upset with me, but I will think about it a bit more carefully after the talk. Yeah. Okay. So if I did this 1n shift, right? This is the only diagram I'm allowed to have because if 1 goes to this side, then there is no pole. If n plus 2 goes to this side, then there is no right-hand side amplitude. Okay, so there's only one thing, very simple. And to do this, I use the fact that there are only these 2 types of 3-point amplitudes, and these amplitudes vanish in Young-Mills. So this is also why this particular configuration is called MHV, maximally helicity violating. And I mean, the way that we think about Young-Mills amplitudes is that every step you take away from MHV, next to MHV, next to MHV, you think of as NMHV, N square MHV, and cube MHV. And those will start having more and more such PCFW diagrams. But note, this is still one diagram compared to, if you'll remember, the Park-Taylor calculation, how many Feynman diagrams that was. So this is definitely simpler, even if you still have to sum over some number of diagrams. Okay. The final thing I wanted to note over here is that when I do this shift, I am choosing to shift the square. Sorry, I'm choosing to shift the angle for n and the square for 1. Okay. And if I didn't do this, I would run into the following problem, which is for 3-particle kinematics in 4 dimensions, you are constrained to either choose all the angles or all the squares to be proportional to one another. And so when I sit on a pole, I don't want to impose any special kinematics for the external particles, because in the end, I have whatever external momenta I have, I want to calculate the amplitude for it. So I need to make sure that this happens only when it's 1 hat, 2 hat, 3 hat. So it's not putting a condition on the external momentum. Good. So now it's very easy to see what happens to gravity, because this is just the full form of the KLT formula. This is actually what the kernel is. Object over here. It doesn't matter what the details are, just that it doesn't involve the momenta n and n minus 1. Right? So now if I choose to shift n and n minus 1 in this formula, I know that these are adjacent. So when I take z to infinity, this will both of these will give me 1 over z. And so that makes it very easy to see that the gravity amplitude, when I take z to infinity, gives me 1 over z square. I can do the BCFW argument for any n point. So this.
Here it must be that this you're getting registered. You're getting a power.
I'm getting a 1 over z.
It's not full string.
This is just gravity.
Not the full string.
Not the full string.
Can you do BCFW of full string? I'm wondering because if you take just large S behavior, it doesn't have the power.
Yeah.
So the complex plane is fine.
Right.
But if you take Regis scaling, it has nice power.
Yeah, I think the z goes to infinity behavior won't be the problem, it will be the poles. So I don't know how many poles you'll get. You'll get some infinite number of poles, and you'll have to factorize on those poles. Because BCFW in the end, you're summing over these factorization channels.
Okay.
And for string theory, you'll have lots of them. So that it just may not be very convenient. I mean, you probably can do it. Yeah. Okay, good. So to just kill the problem, you can use that formula over here and the fact that you understand Yang-Mills scaling to then figure out how BCFW in gravity works for all of the different particles you get when you do the double copy, which is the graviton, the dilaton, and the B field. Okay. Yeah, and these are the results over here. They're very easy, as I said, to see exactly from the double copy. The double copy tells you that recursability is automatic in gravity from Yang-Mills. Okay, so I just wanted to end by telling you where we're going to go in the next lecture, which is recursability. So like the fact that you can use the BCFW relations, even recursion relations, even in gravity is a direct consequence of the double copy and the fact that you can use them in the Yang-Mills.
And you say that again, it's because the Z scaling is good.
Yeah, it's because the Z scaling is good, and you can take the Z scaling from the right-hand side of this equation to the left-hand side very easily. Yeah.
No, I would have a difficult time otherwise.
It's much more involved than in the Yang-Mills case. Yeah. Yes. Yeah. You have to check the Feynman diagram scaling, and also now if you did D, if you were looking at amplitudes with D or B, you'd have to do it again with different Feynman rules. But here, like once you know what's happening with Yang-Mills, you get the dilaton B field stuff for free.
Scaling now you can show for any number of the dilaton B that doesn't matter.
Yeah, as long as it's not all D, all B.
As long as you have at least one, right?
Which actually at 3 level, I think you can't have just one, you have to have at least 2. But yeah. Okay, so Yang-Mills is recursable. There is this BCFW construction. So next time we look at how you can put on-shell stuff together to get the Yang-Mills amplitudes and how much juice you can get out of that, which is related to this story of positive geometry. So that's kind of where we're going next. And yeah, maybe I should end here and see if there are any questions.
Any questions? Not sure there's any Zoom audience. Zoom audience, if you have any questions.
your instance.
I have one quick question. So does double coupling continue to go through with other spacetimes? Specifically, I had in mind anti-disappear spacetime. And if it does, then does that have implications for in the conformal field theory for stress tensor correlation function in terms of the correlation?
So recently, actually, I think in the last couple of years, there's been some effort to extend it to ADS correlators. And I'm not the person who wrote these papers. But my understanding is that you can find some kind of color kinematics. When I say color kinematic, I mean that the numerator satisfies some Jacobi type relation. You can find some color kinematic representation of these correlators as long as what you're scattering has some particular scaling dimensions. So why this matters is because it modifies the propagator, right? And it's kind of like an effective mass. So you need to make sure that those poles cancel correctly and all the locality works out. It needs to be a particular mass that you're choosing. So this only works if you're choosing a particular operator with some scaling dimension to scatter. But in that case, I think they've shown at 4 and 5 point that there is some color kinematic structure and hence some double copy structure. But it's quite preliminary. So this is work by Herd Escape, Radu Royban, Fei Tang, and Xinan Zhao. Yeah, I don't know if I said his name correctly.
There is this flat space element you can take on ATS, where I guess your lead results on double copy would say nothing about stress tensor correlator.
Yeah, though I don't know if it will say anything extra. I mean, at leading order, because it will just give you whatever you expect it to give you. I mean, I don't know if it will tell you anything about the structure outside of that flat space limit. Yeah, because you're kind of saying like it goes in flat. When you take the flat space limit, you're getting something that is well determined. Oh, in the CFT side. So this is unrelated because this is more like DS CFT, but this direction that people have been going in with celestial CFTs, there is a way of writing down color kinematic, whatever the color kinematic representation of certain like gluonic correlators there. So not ADS, not even DS actually, flat space, yeah, flat space CFT, yeah. Yeah, so this is Andrea Pume, Eduardo Casali, and co. Yeah.
That would be some sort of null point limit of 4 stress tensor problems. And that is to be given by this flat space which would relate to current square of current component. So
but you still have, I mean, you still have some contribution from that bulk to bulk propagator, right? That you have to take care of, like a 4 point, like in a Witten diagram, you have a bulk to bulk propagator when you do this. It's not only the contact contribution. You also have a bulk to bulk propagator.
this perfect, I guess you can, the singularity appears will be better on top of each other. Yeah, you can extract out.
But that, yeah, but that will just give you Yang-Mills in flat space kind of, right?
No, but they're saying that at least in the special limit, the 2 CFT correlators are here.
Yeah. Which is novel.
Yeah, I think so. I mean, I don't know if that is the conclusion of those papers. That you'll have to check. Yeah.
Thank you.
Yeah.
Any other questions? Okay, that's actually.
Thanks.